For millennia, humanity gazed upon the night sky, charting the movements of stars and planets, believing what we saw was all there was. Our telescopes have since revealed a universe of unimaginable grandeur, billions of galaxies, each home to billions of stars, vast cosmic structures stretching across light years. This visible universe, a breathtaking mosaic of light and matter, forms the foundation of our cosmic understanding. Yet, this visible spectacle, as astronomers have discovered, constitutes only a tiny fraction of reality. The first whispers of a hidden universe emerged in the 1930s. Swiss astronomer Fritz Zwicky, observing the Coma cluster of galaxies, noticed something profoundly peculiar. The galaxies within the cluster were moving too fast, far exceeding the speeds that their visible mass could gravitationally contain. Based on these velocities, Zwicky calculated that the cluster required significantly more mass than could be seen, a discrepancy he famously dubbed Dunkel Materie, or dark matter. His findings, however, were largely dismissed by the broader scientific community at the time. Decades later, in the 1960s and 70s, American astronomer Vera Rubin and her colleague Kent Ford revisited this missing mass problem, focusing their attention on individual galaxies. They meticulously measured the rotation speeds of stars and gas at varying distances from the centers of spiral galaxies. Classical Newtonian physics predicted that objects further from the galactic core should orbit slower, much like planets further from the Sun. Yet, Rubin's observations revealed a startling uniformity. Stars at the outskirts of galaxies were orbiting just as fast as those closer to the center. This unexpected flatness in galactic rotation curves was a profound enigma. The only explanation, astronomers concluded, was the presence of a vast, invisible halo of mass enveloping each galaxy, extending far beyond its visible boundaries. This unseen substance would exert enough gravitational pull to keep the outer stars in their rapid orbits. This independent evidence strongly corroborated Zwicky's earlier, largely ignored, hypothesis. The implication was clear: the luminous matter we see simply isn't enough to hold galaxies together. Initially, some scientists speculated that this missing mass could simply be ordinary, baryonic matter, perhaps dim stars, gas clouds, or black holes that were difficult to detect. However, extensive observations and calculations based on Big Bang nucleosynthesis, the process that formed the lightest elements in the early universe, placed strict limits on the total amount of baryonic matter that could exist. These limits were far below the amount required to explain the observed gravitational effects, forcing a radical conclusion: the missing mass had to be something entirely new, non-baryonic in nature. And so, the concept of dark matter solidified. It is a form of matter that does not interact with light or other electromagnetic radiation, making it utterly invisible to telescopes. Its presence is inferred solely through its gravitational effects on visible matter and spacetime. Cosmologists hypothesize that dark matter is composed of as yet undiscovered subatomic particles, interacting only very weakly with ordinary matter, primarily through gravity. Its elusive nature makes it one of the most profound challenges in modern physics. Further compelling evidence for dark matter comes from gravitational lensing. Einstein's theory of general relativity predicts that massive objects bend the fabric of spacetime, causing light from background sources to distort and magnify. Observations of galaxy clusters revealed lensing effects far stronger than what could be accounted for by their visible mass alone. This phenomenon acts as a cosmic magnifying glass, mapping the distribution of total mass, both visible and dark, in these colossal structures, unequivocally pointing to vast reservoirs of unseen matter. Perhaps the most striking visual proof for dark matter comes from the Bullet Cluster, a system formed by the collision of two galaxy clusters. Using X-ray telescopes, scientists observed that the hot gas, ordinary matter, from the colliding clusters was slowed down and heated by the impact, lagging behind. However, gravitational lensing maps of the Bullet Cluster revealed that the majority of the mass, presumed to be dark matter, passed straight through without significant interaction. This separation of ordinary and dark matter provided independent and direct evidence of dark matter's existence. Despite overwhelming evidence for its existence, the precise nature of dark matter remains one of science's greatest unsolved puzzles. Theorists have proposed several candidate particles. Weakly interacting massive particles, or WIMPs, were long considered a leading contender, hypothesized to be heavy particles that interact only through gravity and the weak nuclear force. Another class of candidates are axions, hypothetical ultralight particles proposed to solve a different problem in particle physics, but which could also account for dark matter. The search continues across multiple frontiers. The search for WIMPs typically involves highly sensitive detectors placed deep underground, shielded from cosmic rays. Experiments like LUX Zeppelin, LZ, and XANONT aim to detect the incredibly rare instances when a WIMP might collide with the nucleus of an atom in their detector, producing a faint flash of light or ionization. Despite decades of searching and increasingly sensitive instruments, no definitive WIMP signal has yet been detected. This lack of direct observation has led some scientists to question the WIMP hypothesis, prompting a re-evaluation of other dark matter candidates. Parallel to the WIMP hunt, experiments are also rigorously searching for axions. These hypothetical particles are much lighter than WIMPs and would interact even more weakly, often converting into photons in the presence of strong magnetic fields. Projects such as ADMX, Axion Dark Matter Experiment, use powerful superconducting magnets and highly sensitive microwave receivers to listen for these faint photon signals. While the axion remains elusive, the continuous refinement of these experiments pushes the boundaries of our technological capabilities and our understanding of fundamental physics. To date, observations consistently indicate that dark matter outweighs ordinary matter by a significant margin. Current cosmological models, supported by data from the cosmic microwave background and large-scale structure observations, estimate that dark matter constitutes roughly 27% of the total mass-energy density of the universe. This stark imbalance highlights how much of our cosmic reality remains fundamentally unknown, urging scientists to continue their pursuit of this invisible component that dictates the structure and evolution of galaxies and galaxy clusters. Just as the mystery of dark matter was taking shape, another profound discovery began to unfold. For decades, astronomers had known the universe was expanding, a revelation pioneered by Edwin Hubble in the 1920s. This expansion was generally thought to be decelerating due to the gravitational pull of all the matter within the cosmos. The prevailing scientific consensus assumed that gravity, the universe's primary large-scale force, would inevitably slow this cosmic stretching, perhaps even leading to an eventual big crunch where everything collapsed back in on itself. To measure the universe's expansion rate, astronomers rely on standard candles objects with known intrinsic luminosities. Type Ia supernovae, the catastrophic explosions of white dwarf stars, serve as exquisite cosmic distance markers. These supernovae reach a consistent peak brightness, allowing astronomers to calculate their distance from Earth by comparing their observed brightness to their known intrinsic luminosity. By observing Type Ia supernovae in distant galaxies, researchers could precisely measure how fast these galaxies were receding and thus map the universe's expansion history. In the late 1990s, two independent teams, the Supernova Cosmology Project and the HISE Supernova Search Team, began meticulously studying Type Ia supernovae. Their goal was to measure the universe's deceleration. To their astonishment, the data revealed the exact opposite. Distant supernovae appeared dimmer than expected, indicating they were further away than predicted by a decelerating universe. The only conclusion that fit the observations was that the universe's expansion was not slowing down, but was, in fact, accelerating. This groundbreaking discovery shocked the scientific community. This monumental finding earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Their work fundamentally altered our understanding of the cosmos. The implications were profound. If gravity was pulling everything together, what force could possibly be pushing the universe apart, causing its expansion to speed up? Scientists were forced to postulate the existence of another invisible, enigmatic entity, one that exerts a repulsive force on a cosmic scale. This new mystery became known as dark energy. Intriguingly, the concept of a repulsive force within space itself was not entirely new. Albert Einstein had famously introduced a cosmological constant into his equations of general relativity in 1917. He did this to allow for a static universe, as was believed at the time. When Hubble discovered the universe was expanding, Einstein reportedly called the constant his biggest blunder. Yet, decades later, the accelerating universe seemed to resurrect a similar concept, an inherent energy density of empty space itself, subtly pushing the cosmos apart. Unlike dark matter, which clumps around galaxies, dark energy appears to be uniformly distributed throughout space, acting not as particles, but as a property of space itself. It is a form of energy inherent to the vacuum, meaning that as space expands, more dark energy comes into existence, perpetuating and accelerating the expansion. Its precise nature remains unknown. The simplest explanation, echoing Einstein's constant, is a constant energy density of the vacuum. More complex theories, like quintessence, propose a dynamic energy field that changes over time. The cosmic microwave background, or CMB, provides crucial independent evidence for both dark matter and dark energy. This faint afterglow of the Big Bang, observed as slight temperature fluctuations across the sky, contains a treasure trove of information about the early universe's composition and geometry. Detailed analyses of CMB data, particularly from missions like NASA's WMAP and ESA's Planck satellite, have precisely measured the total amount of matter and energy in the universe, remarkably confirming the percentages inferred from galactic rotation and supernovae. With the combined evidence from galactic dynamics, gravitational lensing, type Ia supernovae, and the cosmic microwave background, scientists have constructed a startling inventory of the universe's mass and energy. We've learned that the familiar, baryonic matter, everything we can see and touch, from stars and planets to ourselves, comprises a mere 5% of the cosmos. Dark matter accounts for approximately 27%, providing the gravitational scaffold for galaxies. The remaining, dominant component, about 68%, is the mysterious dark energy, driving the universe's accelerating expansion. This comprehensive understanding of the universe's composition and evolution is encapsulated in the lambda-CDM model, also known as the concordance model. Lambda represents the cosmological constant, or dark energy, and CDM stands for cold dark matter. This model successfully explains a vast array of cosmological observations, from the large-scale structure of the universe to the CMB anisotropies. While highly successful, it relies on two unobserved components, dark matter and dark energy, the very subjects of this investigation, highlighting the ongoing mysteries at its core. The precise nature of dark energy will dictate the ultimate fate of the universe. If dark energy remains constant, as the cosmological constant suggests, the universe will continue to expand at an accelerating rate, leading to a big freeze or heat death. Over unimaginable timescales, galaxies will recede beyond our observable horizon, stars will die out, and the universe will become cold, dark, and empty. Alternative theories, such as a phantom energy that grows stronger over time, could lead to a catastrophic Big Rip, tearing apart galaxies, stars, and even atoms. The discovery of dark matter and dark energy has ushered in a silent revolution in our understanding of the cosmos, revealing that the universe we observe is merely the tip of a colossal iceberg. More than 95% of the universe's mass and energy remains entirely unknown to us. This profound realization challenges our most fundamental assumptions about reality and demands new physics beyond the standard model of particle physics. It underscores the immense scale of our ignorance and the thrilling frontier of scientific exploration that lies before us. Beyond underground detectors, particle accelerators like the Large Hadron Collider, LHC, at CERN are also searching for dark matter. The LHC smashes protons together at nearly the speed of light, recreating conditions from the early universe. Scientists hope to produce dark matter particles in these collisions, which, if created, would not directly interact with the detectors but would manifest as missing energy or momentum in the collision products. While no definitive dark matter particles have been observed at the LHC, these experiments continue to constrain theoretical models. Another approach to finding dark matter involves indirect detection. If dark matter particles annihilate or decay, they could produce detectable standard model particles, such as gamma rays, neutrinos, or antimatter. Space telescopes like the Fermi Gamma Ray Space Telescope have searched for these signatures in regions expected to have high concentrations of dark matter, such as the galactic center or dwarf galaxies. While some intriguing anomalies have been reported, none have yet provided unequivocal proof of dark matter's annihilation or decay. To unravel the secrets of dark energy and dark matter, future space missions are vital. The European Space Agency's Euclid mission, launched in 2023, is designed to map the 3D distribution of up to 2 billion galaxies over a third of the sky. By precisely measuring galaxy shapes and positions, Euclid will use gravitational lensing and baryonic acoustic oscillations to create the most accurate map of dark matter ever produced and to precisely measure the effect of dark energy on the universe's expansion over cosmic time. This is a monumental undertaking. NASA's Nancy Grace Roman Space Telescope, set for launch in the mid-2020s, will complement Euclid's efforts. With its wide-field instrument, Roman will conduct extensive surveys to investigate dark energy's nature through multiple methods, including type Ia supernovae, weak gravitational lensing, and baryonic acoustic oscillations. It will also serve as a powerful probe for understanding the formation and evolution of galaxies, providing unprecedented detail that will help contextualize the role of dark matter in shaping cosmic structures over billions of years. On Earth, the Vera C. Rubin Observatory, housing the Legacy Survey of Space and Time (LSST) camera, will provide an unprecedented astronomical survey. Beginning operations in the mid-2020s, LSST will capture the entire visible sky every few nights for a decade. This colossal dataset will allow astronomers to detect subtle changes in galaxy shapes and distributions, offering another powerful avenue to probe dark energy and dark matter. The sheer volume and depth of LSST data promises to revolutionize our understanding of the dynamic, ever-changing universe. Despite the remarkable success of the lambda-CDM model, certain discrepancies persist, notably the Hubble tension, a disagreement between different methods of measuring the universe's expansion rate. Early universe measurements, derived from the CMB, yield a slower expansion rate than direct measurements from nearby supernovae. This tension suggests either unknown systematic errors in our measurements or, more tantalizingly, new physics beyond the lambda-CDM model. Scientists are rigorously investigating these discrepancies, pushing the boundaries of our cosmological understanding. The lingering mysteries of dark matter and dark energy have also inspired a range of alternative theories. Some physicists propose modifications to gravity itself, suggesting that Einstein's general relativity might break down at cosmic scales, eliminating the need for dark matter or dark energy. Theories like modified Newtonian dynamics, (MOND), attempt to explain galactic rotation curves without dark matter. While these alternatives face significant challenges in explaining the full suite of cosmological observations, they highlight the dynamic and open nature of scientific inquiry. Ultimately, the quest for dark matter and dark energy is a pursuit of a more complete, unified theory of everything. These invisible components point to fundamental gaps in our understanding of the universe's most basic constituents and forces. Unraveling their nature could bridge the chasm between general relativity, which describes gravity in the large-scale universe, and quantum mechanics, which governs the subatomic realm. The implications for particle physics, cosmology, and our very place in the cosmos are truly immense. Dark matter played a pivotal role in the formation of cosmic structures in the early universe. Without its gravitational influence, the small fluctuations in density observed in the cosmic microwave background would not have had enough time to grow into the vast galaxies and galaxy clusters we see today. Ordinary matter, coupled to radiation, was too smooth. Dark matter, however, was cold and could begin clumping much earlier, forming gravitational potential wells that later drew in baryonic matter, providing the crucial scaffolding for the cosmic web. Supercomputer simulations are indispensable tools in the study of dark matter and dark energy. Programs like Illustris and Millennium simulate the evolution of the universe from the Big Bang to the present day, incorporating dark matter, dark energy, and baryonic matter. These simulations successfully reproduce the observed large-scale structure of the cosmic web, the distribution of galaxies, and galaxy cluster properties, providing strong support for the lambda-CDM model and the existence of its dark components. They help visualize processes impossible to observe directly. Behind every groundbreaking discovery lies the relentless curiosity and ingenuity of countless scientists. From Zwicky's initial, solitary observation to Rubin's painstaking measurements, and then to the global collaborations that unearthed dark energy, the human story is one of persistent inquiry. This silent revolution isn't just about cosmic forces, it's about the human mind grappling with the deepest questions of existence, pushing the boundaries of knowledge, and embracing the humbling reality that the universe is far stranger and more wonderful than we ever imagined. Understanding dark matter and dark energy fundamentally reshapes our perception of our place in the cosmos. We are no longer living in a universe dominated by the familiar, but rather in a universe where the dominant forces are invisible, mysterious, and still largely unknown. This new paradigm invites profound questions about the nature of reality, the limits of our perception, and the potential for entirely new physics awaiting discovery. It is a humbling realization, yet one that fuels the drive for further exploration. The journey to comprehend dark matter and dark energy is far from over. Future generations of telescopes, particle accelerators, and theoretical models will continue to probe these enigmas. New discoveries are inevitable, some perhaps even overturning our current understanding. Whether we find the elusive particles of dark matter, precisely characterize the dynamics of dark energy, or uncover an entirely new paradigm, the silent revolution of the universe promises to continue unfolding, challenging us, inspiring us, and constantly expanding the frontiers of human knowledge. This silent revolution teaches us not just about the universe, but about the scientific process itself, the courage to question established beliefs, the rigor to follow evidence wherever it leads, and the humility to accept that vast realms of existence remain beyond our current grasp. Dark matter and dark energy stand as monuments to our cosmic ignorance, yet also as beacons of possibility, inviting us to look deeper, to question further, and to embark on the next great chapter of cosmic discovery. The universe, it seems, still has many more secrets to reveal.